Let's continue with the forests. I've been working in forests for the past 4 years, actually on a very old topic, like dieback of trees. In the 80s and the 90s, acid rain caused major dieback and acidification due to huge amounts of nitrogen deposition. However, recent studies have shown that the pH is not recovering in all these forests, like this one. Also, small birds have calcium deficiency and difficulty in breeding. So the problem is still ongoing. I showed this map from a Nature paper. All the red areas are exceeding nitrogen deposition in the natural areas, which is also the case mainly in the Western European sandbelt, so Netherlands, Belgium, big parts of Germany and Poland. So these sandy soils have acidified the most, and these have acidified so much that we now consider amending alkali materials. So as an agricultural engineer, you would say, let's do some dolomite liming, very straightforward. But we know that it's easy to overdose the dolomite, leading to very fast respiration of carbon. So the microorganisms become very active, leading to carbon loss. Moreover, we have nitrification really being sped up. The nitrogen bomb in these forests goes off, and we get bramble proliferation, as is shown here. So we lose all the biodiversity in the herb layer. That's why this project in the past years has been looking at rock dust as an alternative. We screened multiple products, here Eifel gold from the German Eifel region, phonolite, vulcamin, actimin, soil feed from Norway, the fourth one, and biolite. So the idea is these will dissolve slower and we will not lose biodiversity in the herb layer, but still improve vitality of our forests. And they've been doing that since 2016 on thousands of hectares in the Netherlands, also experimentally in multiple sites, as I show here. So indeed, which mineral you use will be very important on whether it works. So potassium feldspars for a cubed millimeter, the lifetime at pH of 5 is already 600,000 years, so likely too slow in a forest. But there are interesting minerals such as anorthite, which have 100 years lifetime, which is right around the rotational time of a forest. So I will give a very quick overview of my PhD actually. First we go to the short spatio-temporal scale, where we did experiments trying to evaluate the acid neutralizing capacity of these different rock dusts and see whether we can predict the pH increase in mesocosms over time, so over the course of 2 years. This one is published and I presented it 2 years ago, so you can have a look. But the main conclusion was we had these mesocosms that stood on the rooftop for 2 years with the rock dust and 4 soils. We tried to predict the pH using the laboratory-derived rates. So I have, if I can make a pointer, yes. Here the pH measured, and then a model using the total base cation content in the rock dust and the dissolution rates. You see we overestimate after 2 years with our model. However, if we do a suspension test, so just rock dust mixed in with soil, acid soil, and we measure the pH over the course of 1 month, we can estimate available acid neutralizing capacity. And then also using these rate constants derived with automatic titration, we could accurately predict the pH evolution over 2 years. And I've remeasured it currently, and it still actually predicts well after 4 years. So very quick short-term scale. Does it work in a forest now? That was the question. So we had 2 forest sites, and we amended rock dust 10 tons per hectare broadcast, as well as 1.5 kilograms of the rock dust around the saplings. So these were maple saplings. This one is, you can also find it back here. I want to introduce the 2 sites because it will be very important to understand the findings. The first site had a pH of 3.5 measured in calcium chloride, and it was very sandy. So here on this clear cut you can expect water availability to be problematic for trees. The next site was under pine canopy and was a lot more acidic, pH of 3, and less sandy, so we will expect less water problems. So I show here the volume of the maple trees over the course of 3 years. for the different rock dusts, which we also discussed in the previous slides, and also mineral fertilizers and dolomite lime. And I will just take out the significant ones. So in this not so acid forest site, actually it was the water availability explaining the growth. So phonolite vulcamin rock dust has a naturalite mineral, which we showed in the lab, all the rock dusts adding water and then heating the rock dust, that this rock dust can slowly desorb the water. So it actually buffered the drought periods, thereby improving the growth of trees. Dolomite, on the other hand, introduced potassium deficiency because of competition with the calcium and magnesium. We were happy to see that at least it worked in the more acid side, amending the rock dust. And it was interesting to see that even at a huge dose of 1.5 kilograms in such an acid soil, it's still the dissolution rate, so the minerals present in the rock dust, explaining the growth of the trees. So I show that here on the x-axis. You see the available amount of acid neutralizing capacity determined via our soil rock dust suspension test. And this is the volume of the trees. And the same was true for the foliar calcium content of the saplings. So our test improved greatly the prediction compared to just the total base cation content. And now we'll have a look at actual forest applications. For that, I was lucky to find back old German reports from the 80s, so or Dutch reports or Austrian reports, and we revisited these sites from the 80s as well as more recent sites from 2016 and 2019. We always looked at soil chemistry, tree growth, and understory biodiversity. So this one you can find back. It's an Austrian experiment with 5 tons per hectare. I will go step by step. So in the soil we see depth. This is sandy soils in the Netherlands, amended in 2019. Only a significant pH increase with 10 tons of rock dust in the top layer, so the humus layer. Same is true for Eiffel Gold after 7 years, so no significant pH increase. However, after 40 years, we do find a significant pH increase at 30 centimeters, and the increase has also gotten bigger in the humus layer. And we modeled this, but I will not go into detail, but it's totally explained by DOC leaching and the alkalinity which is related to this DOC and that is released actually. So this is the pH increase over all the experiments, and the red line is a DOC generated alkalinity estimate. Then we found a German experiment where they have lysimeters running with 10 tons of phonolite rock dust, and these are cumulative leaching since 1994 of all these elements. Of course, the forest is too acidic to have DIC leaching. This is the pH right below the humus layer, and there we saw huge increases. With that pH of 20 and 80 centimeters, there were no increases, so barely a pH increase, meaning all the inorganic carbon has outgassed. But we did find impressive DOC leaching. I will go into depth. So up to 10, 20 tons of organic carbon that is leached per hectare. In the Dutch side, so these are 8 twin plots. We measured the carbon stocks, so organic carbon stocks. And we actually have litter layers, so the leaves, the humus layer, and then soil up to 1 meter depth. These are the experiments short term, and this is the long term experiment, all revisited last year. And we consistently find huge organic carbon stock increases of 33 up to almost 40 tons of carbon per hectare. So now the question remains, is this organic carbon stable? Where does it come from? Likely root exudation or mineral association. I will look into that in the coming years. Above ground, we can consistently say that tree growth always improved when you remove the limiting nutrients via a mineral that dissolves properly. So in Austria, we had some very high sites. The trees were nitrogen limited at above 2 kilometers. There was no growth response, radial growth, so the thickness of the tree. If there was sufficient nitrogen, the trees responded immediately. So this is really the size of the tree rings every year. It's not cumulative. The graph shows what is formed every year. In the Netherlands, we have applications, and if you remove the calcium or magnesium deficiency, growth is always improved by 50 up to 100%. If you translate this to carbon stock increases above ground, this is another 20 to 40 tons of carbon more. Ecologists are always very scared of amending rock dust in a forest, so we also looked at the herb layer community, and indeed in some cases, in sites which have lower nitrogen status, by amending rock dust you increase the community weighted mean Ellenberg nitrogen value. However, in sites which have huge amounts of nitrogen, we found improvement of the biodiversity and improvement of the Ellenberg R, so reaction value. We always found more plant species, and we never lost any calcifuge species. So these are some of the species that we found. I don't know if I'm over time. I'm really racing through it. So as a conclusion, a rock dust application of 10 tons per hectare can buffer the incoming nitrogen deposition for 10 to 100 years, depending on which rock dust you take and how much nitrogen deposition there is. So this is cumulatively and 2 nitrogen deposition scenarios. And our recommendation for foresters is look at this threshold pH value of 3.2 in the topsoil. Above it, most trees can survive, but below it might be interesting to amend the rock dust, and you can select the rock dust type based on foliar analysis of the existing stand. As a conclusion, it's not a magical solution, but I think it shows great possibilities, and we should all explore organic carbon sequestration in forests in the future. Benjamin has found a report of rock dust application of 120 years old, so that's next on my list to see whether we find some carbon increases still there after 120 years. So I thank all these organizations and collaborators, and I'm open for questions.